Okay, Assalamualaikum and good morning. So we continue our discussion on boundary layer. So now I try to share with you some idea about how to solve turbulent boundary layer by using the idea of empirical form. So the empirical method of predicting turbulent flow quantities on a flat plate with a zero pressure gradient, it is based entirely on data. So the word data here means that it's come from Navier-Stokes equation. So you have equation, so you substitute your variable x and y, the simple one, the simple idea, and then you will get the value of CD, force, and so on and so forth. So it is more accurate than the power law form, but also more complicated. So the time average turbulent velocity profile can be divided into two regions, the inner regions and the outer region. So the time average turbulent velocity profile. So means that here, the idea is we try to plot uh, every molecule's velocity. So this is the general idea, mean by using that equation, what equation means the equation that you derive from Navier-Stokes equation. So if you refer back to your chapter 1 about the differential form, so you could see the idea that actually we try to trace every molecule's properties and then we integrate them to get the total amount. So this is the idea actually. So and then according to the observation, okay, comparing between the numerical and the experimental, it can be divided into two regions. So the velocity profile can be divided into two regions. One is the inner region and the one is the outer region. So normally, okay, I will show this first. Okay, so here you could see the inner region, you could see the outer region. So normally the outer region is about the turbulent zone, the turbulent boundary layer. So it's 100% turbulent boundary layer, but the inner region is actually the starting point with the and until the initial of the turbulent region. Okay, so I will explain about this later. So we go for the notes first. So and then the velocity profile of inner region is defined as this one, U over U tau. So U here means the velocity of each molecule in the velocity profile, and U tau here means the velocity at the wall. Okay. So and then we could determine it as this one, and then another equation comes out. So the U tau is equal to tau naught over rho square root, and we also call this as the shear velocity. Okay, all of these equation actually it's come from the idea of curve fitting. So it's okay, curve fitting means that, okay, I will explain about the curve fitting later on. Okay, so and then uh the research, when you do experiment, you could plot all the data from the experiment, and then you could make a straight line and so on and so forth. So you derive that straight line, you derive that line as equations. So that's why what I mean by curve fitting. So they do the same things. So for the outer region, and then they could say that so the outer region is actually can be shown as this equation. So F if is equal to Y delta. So if you see here, you could find that it is actually the idea of F eta, because to simplify the equation, instead of we use Y over delta, so why not we use Y over delta is equal to eta? Then your equation will become a function of eta. So and then I would like to show you this graph. Okay, what I want to say here is actually, so the simple idea is you do the experiment and then you compare with your numerical, means your calculation based on your Navier-Stokes uh, as you learn in chapter 1. And then for example, the data is like this. Okay, there is a lot of data here. And then what Blasius and his friend did is they try to create a a curve like this, and then maybe the next region of data can be shown as curve like this one. So, and then based on the behavior of this line, so Blasius and all the researchers of boundary layer try to define the equation for that line. So we could say that, okay, the equation for this line is can be shown as this one, and the curve for this line is can be shown as this one. So that's why in this chapter, in the last topic, the empirical form, we just give you the common equation that be used in the empirical form. Okay, so we not derive the equation, but the story is we are using Navier-Stokes equation. We plot, we do the validation in experimental works. So from the graph, so there is a lot of data, and you start to draw your fitting, your curve. So some in some textbook they will call that the best curve fitting is the final equation. So this is the works of Blasius and his friend. And finally, you could see here, the equation above involve the shear velocity, U tau, which depends on the wall shear stress. There are several such relationship used. One that gives excellent result is shown like this one. Okay, this is the meaning of there are several relationship used. So if you read about this one, read about the Blasius and his friend to conduct the evaluation of boundary layer in turbulent region, we'll find that it comes 2 or 3 equation being proposed. But in our textbook, we are referred to Porter textbook. In Porter textbook, we are using this equation. So it is okay for you just to remember that if the question asks you to solve problem of turbulent boundary layer by using the numerical or by using the empirical form, okay, please take the value of CD is equal of this one. Okay, CD is equal to 0.455 over ln in bracket 0.06 Reynolds number x square. Okay, so in some textbook, they will call this CF is equal to local skin friction coefficient. So according to my notes previously, so the CF here is actually equal to the CD, the local friction coefficient. So this local skin friction coefficient or local drag coefficient allow us to determine the tau naught and U tau at any location of interest. The velocity profile can be used to calculate quantities of interest, but U tau must be known. So, and then assuming turbulent flow, the leading edge, the shear stress can be integrated to yield the drag. Then the skin friction coefficient or the drag coefficient becomes this one, 0.523 over ln 0.06 Reynolds number square. So this relation is very good and can be used up to Reynolds number 10 to the power of 9 with an error of 2% less, or even at Reynolds number 10 to the power of 10, so the error will just 4%. So we will see some calculation to show the difference between the power law form and the empirical form in terms of the difference of the answer. So mean that the error percentage here. So what we could conclude here is actually if you are solving a very high Reynolds number, means the turbulent might be more than 10 to the power of 9, you are advised to use the idea of numerical form. So empirical form. So instead, you are assuming your turbulent boundary layer velocity profile as power law form, mean what y over delta by the power of 1 over 7 or 8 or 9, something like that. So, and then finally, we could summarize this equation as U over U shear U tau is equal to 2.44 ln U tau delta over nu plus 7.4. 4. So this equation allows an easy calculation of delta by knowing the value of u tau. So, and then this is actually the kinematic viscosity. So this is not velocity, this is a kinematic viscosity. Please remember this equation carefully. Okay, just remember this equation to solve the problems. So, okay, so we will discuss some tutorial from the textbook. You may get this from the textbook. So example 1, estimate the boundary layer thickness at the end of 4.5 meter long flat plate if wind flow on it at 30 meter per second. Also calculate the drag force on one side if the plate is 3 meter wide. Use the empirical data. Assume that the temperature is 20 degrees Celsius. So, so first, okay, from here, this is the last page of our theoretical notes. So means that this is the last syllabus of our boundary layer.